Welcome to the Deep Dive, where we plunge into fascinating research and pull out the insights that truly matter.
Great to be here.
Today we're taking a bit of a visual journey, thinking about those incredible fluid forms you see in modern architecture.
Ah, yes, the curves.
Exactly. Those sleek, sweeping skyscrapers, buildings that seem to sculpt the air. They're moving away from those rigid straight lines.
Right, embracing curves to show motion, rhythm, continuity. It makes the buildings feel alive almost.
Totally. They aren't just functional structures anymore. They feel like expressive works of art, really defining our skylines.
And what's really fascinating, or maybe challenging, is that while these curved elements, especially these nonlinear columns, look amazing, they're a huge headache for engineers.
A headache. How so?
Well, unlike your standard straight column where the load path is pretty predictable, straightforward,
Yeah, force goes down.
pretty much. With these complex curves, the way forces travel through them is much more complex. Their response is highly nonlinear.
Meaning they don't just bend proportionally to the load.
Exactly. And frankly, the standard design codes, they offer very limited guidance for these kinds of innovative shapes. It's a real test of engineering ingenuity to make them safe, not just beautiful.
Absolutely. So our mission today in this deep dive is to unpack a really pioneering numerical study.
Okay.
We're zeroing in on the behavior of double-curved, hollow steel columns. Specifically, what happens when you push down on them, actually compress them.
Right. The hollow ones, double curve, that's quite specific.
It is. And this research is like a shortcut, It helps us understand the critical structural implications, the design principles you need to actually build these things safely.
So we can have those inspiring architectural forms without unexpected problems.
Precisely. We're going to uncover what makes them strong, what makes them fail, and crucially, how engineers can optimize the design, balancing that breathtaking beauty with, well, unyielding safety.
Okay, sounds good. But to really appreciate what's new here, we probably need to set the stage a bit. What did we know before this study?
Good point. There has been research on curved things, right?
Oh, absolutely. A lot of excellent work. Engineers have looked at curved structural elements from different angles. For instance, there have been finite element simulations on hollow steel sections, HSS columns,
Okay.
looking at things like slenderness, initial loads, how they affect collapse. Some parametric studies even found rectangular profiles often carry more load than circular ones in polygonal HSS.
Interesting. What about concrete-filled ones? I feel like I've heard about those.
Yes, curved concrete-filled steel tubular members, or CCFST. There's experimental work showing they can be quite ductile, maybe even carry slightly more load than straight ones, surprisingly, even with imperfections.
Huh. More load, even though they're curved?
Slightly, yeah. And similar findings for concrete-filled stainless steel tubes, too, though they tend to fail by global buckling.
And we also know a fair bit about arches, don't we? How they buckle, boundary conditions, loading, all that stuff.
Definitely. A lot of work on arches, how pre-buckling deformation matters. And people have even shown you can cast double-curved concrete columns using flexible forms, which is pretty cool architecturally.
So lots of groundwork laid.
Exactly. But here's the gap. Despite all that great work on straight or just mildly curved or concrete-filled elements, the actual structural implications, especially the really complex nonlinear behavior of double-curved hollow steel columns.
A specific focus of this study.
Right. That's remained largely unexplored territory. So this study we're diving into, it's essentially the first in-depth numerical look. Load-bearing capacities, failure modes, how they deform under load for these large-scale, double-curved, hollow steel columns. It's filling a pretty significant gap.
That makes perfect sense.
Yeah.
So, okay, if you can't just go out and build, dozens of these huge, complex columns to take them physically, how do the researchers get their answers? You mentioned numerical study. They built a kind of digital twin.
Precisely. A virtual version. They developed a comprehensive, three-dimensional, 3D finite element model using commercial software, ABAQUS. Think of it like building a perfect digital replica of the column.
A digital lab. I like that.
Oh.
So you build this virtual column and then you can, crush it, bend it, all inside the computer.
Exactly. Put it through its paces virtually.
Got it.
And because they expected really non-linear behavior, we're talking large displacements, the steel buckling locally in progressive ways, how it behaves after it starts buckling.
Stuff that's hard to predict with simple math.
Very hard. So they needed a special tool. They used something called the ABQUS explicit solver.
Explicit. Sounds dynamic.
It usually is, yeah.
Yeah.
Often used for simulating things like car crashes or impacts. But it's actually excellent for these kinds of complex quasi-static problems, too. Problems with severe nonlinearities where the traditional implicit solvers might struggle or fail to converge.
Quasi-static meaning slow loading, like in a real building.
Right. It's like using a high-speed camera to analyze something happening in slow motion. It captures every tiny detail of the deformation process, even when it gets really complicated.
That's a great analogy.
Sure.
But how do you make sure these digital stress tests are actually realistic? That it's not just some weird computer artifact? How do you maintain that quasi-static control you mentioned?
That's where the rigorous process comes in. They were very careful. For example, they did modal analysis first to pick the right analysis time long enough to avoid dynamic effects you wouldn't see in reality.
Okay.
They applied the load, the displacement, really smoothly using a specific amplitude curve, no sudden jolts. And crucially, they kept a close eye on the kinetic energy in the model.
The energy of motion.
Yeah. They made sure it stayed way, way smaller, like an order of magnitude smaller than the internal energy, the energy stored in the deformed steel. This confirms the column's response is driven by the actual deformation, not by inertia effects.
Got it. So it's truly mimicking a slow crush.
Exactly. And the model itself included both geometric nonlinearity, so it accounts for big changes in shape, large rotations, and material nonlinearity.
Meaning how the steel itself behaves.
Right, how it yields, stretches, gets stronger up to a point, that inelastic response. They use specific elements, too. Four-node, doubly curved shell elements, S4R, which are really good for complex curved shapes.
What about things like tiny imperfections in the real steel or stresses locked in from manufacturing? Did they include those?
Interestingly, no. They deliberately excluded initial geometric imperfections and residual stresses.
Why is that? Don't those usually matter?
They can, but based on previous validated studies, these factors tend to have a pretty limited influence on the global response, the overall behavior of these kinds of compact elements with uniform curvature. It simplifies the model without losing the main picture.
Makes sense. Don't add complexity if it doesn't significantly change the big answers.
Yeah.
But, okay, the model sounds sophisticated, but it's still a model. How did they prove it actually matches reality?
Validation, right. Absolutely critical. You can't just trust the model blindly. They rigorously validated it against existing experimental findings.
Real-world tests.
Yes. They used data from axial compression tests done by Kalkali and colleagues on cold-formed square steel tubes that had intentional double curvature. Real columns, real tests.
And did the digital twin match up? How close did it get?
It held up very well. The validation showed a strong correlation, as they put it, both in terms of the overall load versus displacement curve, and importantly, the failure modes, how it actually buckled and collapsed.
Strong correlation. What does that mean numerically? Was it perfect?
Not perfect, no simulation is. The ultimate load predicted by the model differed from the experiments by about 11% to 24%.
11 to 24%. That sounds like a bit of a range. Is that considered good for this kind of simulation?
It actually is, yeah. For highly complex nonlinear simulations like buckling, where tiny real-world factors can have a noticeable effect, that kind of agreement is generally considered quite reasonable. It indicates the model is capturing the essential physics correctly. And crucially, the model predicted that plastic collapse. The permanent yielding and buckling would start right at the transition zones where the straight parts meet the curved parts. And that's exactly what the experiment showed.
Ah, okay. So the location of failure matched too. That builds confidence.
Definitely. It gave them high confidence that their digital lab was reliable for exploring further.
Fantastic. So with this validated digital twin, they could then unleash it, right? Run a whole bunch of virtual experiments.
Exactly. That's the power of simulation. They conducted a comprehensive parametric study. Imagine building hundreds of these columns virtually, tweaking one thing at a time.
How many columns?
Full-scale ones. 4,000 millimeters long, so 4 meters, with a 2-millimeter wall thickness. And they systematically varied key geometric parameters for both square and circular hollow sections.
Okay, what parameters did they look at?
Things like the cross-sectional width or diameter, the curvature angle itself, the radius of that curvature, and something called the end parts offset, which is basically how much straight section there is at the ends.
Right. Lots of variables. So let's dive into the secrets. What did they find? Let's start with the curvature angle, theta. How much does bending the column more sharply actually affect things?
That's a critical one. And the big takeaway, increasing that angle significantly compromises the load-bearing capacity. for both square and circular sections.
Significantly, like how much?
Well, for the square sections, going from their baseline, say, to 25 degrees, dropped the max load by about 20%, go up to 35 degrees, and it's down over 40%.
Wow.
And for circular sections, it was even more dramatic. Almost a 60% drop in load capacity at 35 degrees compared to the gentler curve baseline.
60%. That's huge. Does it affect stiffness too? Like how much it deflects initially?
Yeah, the elastic stiffness definitely took a hit as well, especially noticeable in the circular sections as the angle increased.
So why? Why does a sharper curve make it so much weaker?
It boils down to amplifying what engineers call second-order effects.
Okay, explain that a bit.
Imagine the column under load. It starts to bend a tiny bit just because of the curve. These second-order effects are when that initial bending creates additional sort of leveraged bending moments. The more initial curve, the bigger these extra moments get, and the whole thing becomes much more prone to global instability. It just wants to buckle more easily.
Like a multiplier effect from the initial geometry.
Precisely.
Right.
And the failure modes changed quite dramatically, too. At lower angles, stress might start in the straight parts, then move to the curves before buckling.
Okay.
But at higher angles, like 30 degrees and especially 35 degrees, they saw this distinct tripartite local buckling pattern.
Tripartite, 3 parts.
Yeah, imagine the column crumpling locally, like little dents forming,
Yeah.
in 3 separate places almost simultaneously, usually in the 2 curved regions and one of the straight end regions. It's a complex failure mode.
And this happened for both square and circular at high angles.
Yes. Which strongly suggests that once the curvature gets really high, that geometric instability it causes starts to dominate over the differences in the cross-section shape itself.
So, practical takeaway for an architect or engineer listening. If you push the curve too far, the inherent weakness from the curve itself becomes the main problem, almost regardless of whether it's square or round.
That's a good way to put it. It's a fundamental trade-off. That dramatic visual sweep comes at a structural cost. Decreasing the curvature angle, making it gentler, lets those straight-end segments help carry the load more effectively. It improves the stress distribution, makes it more stable. It's about finding that balance.
A really key insight about the angle itself. Okay, what about the physical size? The transverse dimensions, width or diameter? Does a thick column behave differently from a thin one, keeping other things constant?
Another great question. And yes, the dimensions have a distinct impact. And here, the general finding was that square sections seemed to perform a bit better overall.
Better how? More load, stiffer.
For the square sections, making them wider led to a moderate increase in the peak load they could carry, maybe 5 to 10%. Making them narrower caused a slight decrease. But crucially, their stiffness didn't really change much with width.
Interesting. Consistent stiffness. What about the circular ones?
Quite different. Circular sections showed a pretty clear reduction in maximum load as the diameter got smaller, ranging from 11% down to a whopping 71% decrease for the smallest diameter tested. And unlike the square ones, their stiffness did degrade progressively as they got thinner.
So square holds its stiffness better as size changes. Circular gets floppier and weaker, much faster when it gets smaller.
That's a fair summary. Looking at the failure modes, stress tended to start near the ends, then move to the curved parts, similar to before.
Okay.
But how it buckled was interesting. The circular profile often developed this progressive buckling wave, kind of a stable collapse after yielding. The square ones showed similar behavior, but the buckling might concentrate in a different area.
And you said square performed better.
Well, the square specimen that actually held the highest load in this part of the study, it failed by buckling in one of the straight end segments, not the curve.
So making the square section bigger and stronger pushed the failure away from the tricky curved part.
Exactly. It suggests that increasing the transverse dimension, especially for square sections, can shift where the stress concentrates, potentially moving the failure to a less vulnerable spot, which lets it carry more load overall.
So you can sort of control where it fails by playing with the width.
To some extent, yes. But it's also important that while changing the dimensions clearly affected the load capacity, it didn't fundamentally change the type of failure mode, just maybe where it initiated.
Right. So square gives you more consistent stiffness, better load capacity, especially when wider, and maybe some control over failure location. Powerful stuff for design. Okay, now for something you hinted might be surprising. The radius of curvature, R. If the angle is critical, surely how tight that curve is must also matter a lot.
You'd think so, wouldn't you? But what they found here was fascinating. within the range they tested, which was from a 500 millimeter radius up to 1100 millimeter.
So from a fairly tight curve to a much broader one.
Right. The effect on the actual axial capacity, the maximum load, was surprisingly minor. Peak load variations were less than 2.5%. Less than 2.5%. That is surprising. So whether it's a sharp bend or a gentle sweep, it holds roughly the same maximum load.
In terms of peak load, yes. The columns showed, as they put it, remarkable consistency in their overall structural response. Pretty much the same elastic stiffness, similar nonlinear deformation curves, fairly uniform stress patterns, regardless of the radius in terms of that ultimate capacity.
Wow. Okay, that goes against intuition a bit. But does that mean the radius doesn't matter at all then?
Not quite. This is the crucial part. While it didn't change the peak load much, the radius of curvature significantly modified the failure mechanisms
So.
by changing how the stress concentrations redistributed themselves during loading. For instance, one square column with a smaller radius, a tighter curve, actually showed stress migrating from the upper curved part down towards the lower straight part as load increased. That's not what you might typically assume.
Huh. Stress moving away from the tighter curve. Yeah. And conversely, a circular column with a larger radius, a gentler curve, ended up failing through a complex dual hinge mechanism. It formed plastic hinges, those points of permanent yielding and rotation, in both a curved section and a straight section simultaneously.
A plastic hinge being where it permanently kinks, essentially.
Exactly. It's where the major deformation happens before final collapse. So the radius dictates where these hinges form, how the column actually breaks down, even if the peak load it reaches just before that point isn't drastically different.
Okay, so the design lesson is don't ignore the radius. Even if it doesn't slash the ultimate strength number, it fundamentally changes how the column behaves under extreme load and where it's likely to fail. That's critical for predicting behavior and ensuring safety margins.
Precisely. And it also reinforces the idea that those straight end segments, the offsets, play a key role in managing stress.
Which brings us neatly to the last parameter, the influence of offset distance at column ends, D. This is the length of those straight bits at the top and bottom, right, before the curve starts.
That's it. The distance between the very end of the column and where the curve begins, the inflection point. And this one. This turned out to be perhaps the most sensitive parameter they looked at.
The most sensitive, more than the angle or the width.
In terms of performance degradation, yes. They found that reducing this offset distance significantly hurt performance.
How significantly?
While shortening the offset they tested from 1,000 millimeters down to 400 millimeters led to a peak load reduction of 13% to 21% for the square sections.
Okay, noticeable.
And for the circular ones, it was even more pronounced, a 15% to 37% drop in load capacity just by shortening those straight end pieces.
37%. Just from having less straight bit at the end? Wow. Did stiffness suffer too?
Yes, a progressive reduction in stiffness was seen as the offset got shorter. Again, particularly for the circular sections. There's a clear inverse relationship there. Shorter offset, less stiffness.
So why is this offset so critical? What's happening structurally?
It seems to be all about localized damage. When the offsets were shorter, especially the 600 millimeter and 400 millimeter ones, the failure mode consistently involved the development of plastic hinges at both of the curved regions, B and C.
So both curves started to yield and buckle.
Yes, for both square and circular sections when the offset was short. It implies this fundamental response. A shorter offset effectively increases the intensity of the curvature right near the ends, it concentrates strain there, and it means larger bending moments get transferred directly into those critical curve transition zones.
Making them much more vulnerable.
Exactly. The circular specimens with short offsets showed a more ductile failure, lots of plastic deformation, but it was all heavily concentrated in those curved zones. The damage localized right there.
So the design implication is pretty clear then. You need a certain amount of that straight end section. Don't skimp on the offset.
Absolutely. There seems to be a threshold. Go below it, and those straight segments become much less effective at resisting the load. The stress gets dumped right into the curves, and your overall stability plummets. Getting that offset dimension right is critical for safety and durability.
Wow, what a detailed picture. It really feels like we've journeyed through the structural secrets of these amazing curved forms. We've navigated the complex world of double-curved, hollow steel columns.
Yeah, uncovering just how much that geometry dictates their behavior.
And this study, being a pioneering numerical investigation, it really confirms that these elegant architectural shapes demand a Well, a very nuanced and data-driven understanding from engineers. You can't just eyeball it.
Definitely not. And what's great is that this research provides a kind of blueprint, some clear guidelines for designing better buildings with these elements.
Let's recap those core implications then.
Okay. First, square cross-sections generally seem to offer superior axial strength compared to circular ones in this context.
Right. Square is often stronger.
Second, the curvature angle and the transverse dimensions width or diameter are critical. They directly influence how stress builds up and moves through the column.
Angle and size matter a lot.
Third, the radius of curvature, surprisingly, has only a minor effect on the ultimate load capacity. But, and it's a big but, it significantly alters the failure mechanisms, where and how it breaks.
Don't be fooled by the peak load number.
Exactly. And finally, that end offset distance. It's the most sensitive parameter. Reducing it substantially degrades performance and basically invites instability.
Keep those straight ends sufficiently long.
That's the key. So for optimal performance, what you're really looking for is a combination. Relatively small curvature angles, larger transverse dimensions, especially if square, and sufficiently large end offsets.
And the goal of that combo
Is to try and prevent failure starting in those beautiful but vulnerable curved zones. Ideally, you want to confine any buckling to the straight terminal segments. Make it fail predictably if it has to fail.
making them both stunning and robust.
That's the aim. This work really lays a solid foundation, I think. It helps bridge the gap between complex architectural vision and sound engineering practice for these kinds of load-bearing systems.
Balancing form and function in ways that maybe seemed too risky before.
Potentially, yeah. It gives engineers more confidence and better tools.
So as we wrap up, let's leave our listeners with a thought. As we continue to push the boundaries of architectural design, seeing ever more fluid and complex shapes, what new possibilities really open up when we can fully harness the structural potential of these non-prismatic, double-curved columns, armed with this kind of knowledge? How might these insights influence that next generation of iconic, fluid, and hopefully very robust buildings that you see going up around you? Maybe it gives you a new appreciation for the hidden engineering challenges behind all that architectural beauty.